Hello, everyone. My name is Chase Sheldon, and I am joined by Arjun and Nagasai, and we will be going over a group video presentation for next slide. So for the agenda, we have the first research paper, which is Learning Real-Time A-Star Path Planner for Unmanned Air Vehicle Targeting Sensing. And for paper two, we will be discussing the simple sub-goaling for real-time search. Next. I'll be discussing the first article, which is Learning Real-Time A-Star Path Planning for Unmanned Air Vehicle and Target Sensing. This article gives a look into path planning system for closely spaced targets from the perspective of unmanned air vehicles, which are also known as UAVs. The planner for these systems relies on a search algorithm called Learning Real-Time A-Star algorithm, or LRT A-Star for short. This algorithm produces all candidate paths that accomplish the objectives in the shortest possible distance. Primitive turn and straight turn sections of a particular step size are used to create a tree of possible paths. This is done with the starting node being the starting position of the UAV. The LRTA star searches the tree to find the feasible minimum length paths at any given point in time. The parameters used in LRTA star directly influence execution time and minimum length paths. To improve upon the LRTA star, a modified LRTA star algorithm can be used that stops execution when there's no continued improvement in paths after a specified number of execution steps. This algorithm produces short distance paths in an optimized amount of time. Next slide. Path planning has been used in autonomous vehicles. In autonomous fixed-wing aircraft, there are some unique things to consider. The path planning is more complicated because there are some limitations of aircrafts. One of these limitations is the turning radius constraints of the aircraft. Aerial sensing must also be done from ground targets or foreground targets and requires a footprint of the sensor to pass over groups of targets. This means that the path planning must not only include the aircraft's attributes, but also the sensor footprint along as it sits along the path. The difficulty of path planning tends to go up the closer that targets are together. This is because the aircraft has a limited turn radius, so more aggressive measures must be taken. For the work that we'll discuss today, we will focus on a path planning method for sensing closely spaced targets that utilizes the planning flexibility of the sensor footprint while considering the aircraft dynamics to produce an optimal minimum path to view all the targets. Next slide. There are three things we need to consider to address the problems of developing the system. The first is coupling between path segments. The second is the sensor footprint, and the third is the viewing order of the targets. The typical approach of planning paths is to consider shortest path segments from one point to the next. This works well whenever spaced apart. However, it has limitations as objects get close together, and this can result in less than optimal path. This can be seen in figure 1, where the optimal path to the first target sets it up for a poor position for the second target, and this continues between the third and fourth target. This means that the sum of all paths is suboptimal, even though the point-to-point is optimal. In figure 2, we can see that the optimal multi-target path is much more efficient than the point-to-point. This is because it looks at the subsequent sections and sets up the path to make it optimal overall, even if the point-to-point isn't optimal. Most path planning approaches have paths that fly directly over targets to view them. This is restrictive and unnecessary. A path can be better optimized in many cases if an optimal path is considered that still puts objects in a viewable location while still considering the best overall path. It is not always necessary to view targets directly from above. The final challenge of this approach is the viewing order of targets in close proximity. An effective approach to this requires a planner with the ability to plan optimal paths through multiple targets while utilizing the sensor footprint to its full ability, but not necessarily flying over the top of targets directly, and also determining the viewing order that results in the minimum length path. To meet these requirements, an implementation of the LRTA star search that approximates these optimal paths is used. Next slide. Trajectory research has been done in many areas such as vehicle systems and robots that has led to many new path planning techniques. These techniques are useful, however, most of them only consider a path where the start and end point are defined. This is not the case in the scenario that we're looking at, where the UAV must pass within a viewing vicinity of multiple targets with no defined end state. This new algorithm configuration uses ideas from Dubin's principles, which prove that the minimum path connecting two positions consists of a turn followed by a straight segment followed by a turn. Turns are made at the minimum possible turning radius of the vehicle. Using these principles, an optimal traveling salesman solution has been considered where the worst case length is bounded. There has also been a hybrid A-star and automation approach to an online UAV path planner that utilizes the Dubin's primitives. Another related path planning approach is the probability roadmap, or PRM for short. PRM randomly selects configurations and from a configuration space and plans paths to those configurations. After randomly searching for a specified time, a roadmap can be constructed that approaches and even sometimes finds the shortest possible path. The idea is that PRM will approach upon the optimal path as time continues. A similar approach to PRM is rapidly exploring random trees, or RRTs for short. RRTs randomly selects points within the search space and continues to construct a tree of dynamically feasible points. The tree continues to be developed until the goal is reached. The control inputs are tracked and then used to develop an open loop control input sequence from the starting node to the end node. Some variations of this algorithm have been successfully used to plan point paths for small UAVs in flight simulations. One path algorithm that has been used in aircraft applications is the Mixed Integer Linear Programming, or MILP for short. MLIP can be used to produce paths that avoid collisions while linking starting and end states. Typical implementations of this have seen early convergence issues. However, they are relatively well suited for addressing task assignment and path planning simultaneously. Next slide. In order to have a successful path planning algorithm, the algorithm must produce a path that is not limited by endpoints and utilizes the entire capability of the sensors. These capabilities are provided by discrete step paths, which are made by combining the primitive turn and the straight segments in order to make a flyable path. The choice path is decided by the specific objectives of the path. For this to work, each primitive segment in a discrete step path is of a particular length and is either a turn, which is made at a minimum turn radius, or a straight line. This follows the Dubin's path principles. By assembling the primitives of left turn, right turn, and straight primitives, we can create a tree of flyable paths. Then the path planner can search for the branch that accomplishes the objectives in the shortest distance. It is apparent by the tree seen here that the shorter steps increases resolution and the longer steps allows deeper trees which have better convergence. Step length and depth have a dramatic effect on path planning speed and the quality of the resulting path. The simplest approach is to generate a fixed depth tree that uses existing memory sources of the system. The configuration of the vehicle at a given node is P equals X, Y, V, where X and Y represent the internal position or the inertial position, and V is the vehicle as it is measured from the north. The vector of the vehicle to the target of I is D of I. The configuration of child node is calculated by the change in the heading. Targets are sensed if they are within the vehicle's sensor footprint. The algorithm is capable of sensor footprints of arbitrary size. The discrete step paths are limited to 2 dimensions, which reduces computation complexity. These concepts, however, can be extended to 3 dimensions in a relatively easy manner. Next slide. Now I'll hand it over to Arjun to continue discussion.
Thank you, Jess. Thank you for the introduction. My name is Arjun Yadav Matapalli. I'm a graduate student, Computer Science Department. Now I'm going to discuss about the learning real-time A-star research algorithm. The learning real-time A-star is known as LRTA research. For determining, it is to determine which branch of defined path is best achieves the results. Like it is used to resolve the path planning challenges which we have to get the desired targets. Like the target might be single or multiple. It may be used for any sort of the world, like includes grids, trees, or different graphs. It is superior to the A-star search algorithm in terms of memory space because it needs less memory compared to A-star. When utilizing this algorithm, the execution speed is compromised to decrease the search spatial complexity. This algorithm is simple and effective. This is a basic simple algorithm for the LRTA star research. Here, the current node heuristic value is updated at each iteration to get the desired result. Delta H total is the total heuristic change which the algorithm runs on, and the count is the length of the current path. Best count is the length of the best path which found by the object, and sensed indicates whether the target have been sensed or not. Based on these factors, these algorithms runs. The initial heuristic is that, as I told that, based on the change in value of the heuristic, this algorithm works to sense the targets. The path, target path overestimates the distance to the distance. The search may never reach that node. Then the algorithm it terminates and it says that the path may not be found. Initializing the heuristic to 0 might be permitted, but the learning path would take a lengthy time. This is the simple example to demonstrate and to calculate the initial heuristic value. For case 1 to the left, the distance, like for finding the distance which is farthest from the target, this function h is equal max modulus di by sensor by 2, like half of the sensor distance. And to the right, this function is similar, but it deducts the distance. Like for single target, it deducts half of the sensor width, and for multiple targets, like shown in right, target 1, 2, 3, what it deducts from the heuristic value is that it deducts the target, nearest target, half of the nearest target value, and it calculates the second nearest value distance, and it deducts the value, and it updates the heuristic value from this. The terminating conditions for this case is that the strategy used to end the tree search has direct impact on the tree search speed and the path length performance. As long as the search continues, the path length improves, and it depends on the speed and the path length. Based on these two factors, the efficiency in the execution time, it depends to choose the target, and it gives the best path to reach to the target. If for more iterations, for better path length, it will be like higher running time is required, because it needs some time to get to choose which target, like to choose the best target path to reach. For LRTA star, like this is the other one, non-improving LRTA. It is NI LRTA star. This method is it is it is in termination condition. And these two are the simple paths generated by these two algorithms. Left is LRTA star and the other is NI-LRTA. Here we can show that the path plan is like the left, it is having 5.29 is the total path length to reach the target, and to the right it is 5.49, which is achieved by NI-LRTA. So that we can it can be concluded that the path length taken by LRTA star is less compared to the other one. And the branch terminals for LRTA search tree, the memory management and path tree trimming are very they operate well. The current node is terminated by removing its children, and the historic value can be updated to infinity. Like it can go till infinity, but we cannot get the infinity value in practical, but it can be optimized while doing it by using the root nodes. All of the node childrens have heuristic values of infinity. Like I said, the nodes which is dead or end, it may terminated in the same way. Path tree size. For the path tree size, the size of the path tree is the key issue while searching for the best optimal path. The size of the tree grows very fast as the step size lowers, and making the tree time consumption. It takes time to like for every change in step size, it takes some time. The whole root tree is in third size, 3. The size of the whole root is 3D. That means if D increments the whole number of nodes the loop, the path takes, it increases the number of nodes so that the execution time. Reducing the depth of the path tree before the search begins is the most effective way to limit the size of the search path to accomplish the best results and to reduce the execution time. Finding a single source potential field path planning method is the best way to get the LRTA search tree algorithm. And the source for this technique is the target that is closest to the vehicle, and the potential field algorithm plot a path to the target. Once the first target has been reached, the source is chosen from the next closest targets. And this technique is repeated until it reaches all the goals. The LRTA algorithm has the benefits of allowing new goals and limitations to be readily put on the path. The step size selection is the vital thing. Like, depends on the step size, the algorithm memory size and the time required for the algorithm to reach the target depends. Choosing a small step size is the best approach to get the global optimum value. Bigger step size considerably enhance the algorithm running time with only a tiny increase in path length. Testing and comparison. Like for this test in the paper, they have taken 2000 targets. For this situation, they compare both two algorithms, LRTA star and NI-LRTA star. Each scenario includes 3 targets, and the tests were composed on Linux operating system with CPU 512 MB of RAM. And LRTA search tree algorithm running time and path length performance are directly affected the step size. Raising the step size decreases the algorithm running time, while just slightly increasing the length of the resultant path. These two are the validations of LRTA search tree. This is the path which it follows, the pinpoint sensor footprint, and the other is the footprint. With LRTA, it utilizes large sensor footprints. It produces that 33% short length compared to the other one. The path length, here the graph shows that it compares the two different search algorithms. Here we can see the step size step size increase at 0.45 and 0.5 in x-axis, and the distance is in y-axis. When the step size when the step is linear, so the both the algorithms follows the same distance path. When the step is at 0.45 to 0.5, there is a steep drop, or else from 0.5 there is a steep rise in the step size, so that both algorithms follows the same distance path. These are the running times for both the algorithms, increasing step size. We can see that from figure A, both the algorithms, like for less number of targets, the nodes visited by each scheme is different. For less number of targets, for figure A, for 0.2, it is rising till 10 power 6. It's huge number. In the other case, for at 0.2, it is at 10 power 6, near to 10 power 6. That means the number of nodes visited by this LRT algorithm is very less compared to the other. And these are the pictures for differentiating the number of targets. Based on the number of targets, these two, like in figure A, running time versus number of targets. X-axis, we have given the number of targets, and the right mean node visited and the length of the path. When the number of targets are getting increased, so that the LRTA search algorithm goes through more number of nodes compared to the NI-LRTA. Whereas if we take mean path length, the LRTA search algorithm is having less shortest path compared to the counterpart. To conclude, in this paper, in this part, they compared two such algorithms, and it can be the resultant shortest path depends on the steep length of the curve. The LRT algorithm always generates the shortest path, but it takes more time. And coming to the other one, NI-LRTA achieves successful trade-off between path length, performance, and the quicker running times. These algorithms plan optimum and near optimum pathways. Both algorithms provide reasonable solutions. Both have some advantages and disadvantages, but they do produce fruitful results, as well as the ability to include range of goals and limitations. Thanks, and Charan will continue.
Hey Arjun, thanks for the introduction. So I'm going to go through the second paper, that is KNN LRTA Simple Subgoaling for Real-Time Search Star. This was written by Vadim and Agni. This was actually part of proceedings of AAAI Conference on Artificial Intelligence and Interactive Digital and Entertainment. Can we go to the next slide? Coming to the abstract. So as a solution to the primary problem of implementing state-of-art real-time search algorithms in video games, they have actually created a more straightforward and more memory efficient technique for pre-computing subgoals. Over the course of 8 video game maps, the new technique used actually roughly 9 times less memory than the standard DLRTA star, while producing answers that were just 9% worse than the previous method. Can we go to the next slide? So in the introduction, the video games, it is a common for players to have difficulty from moving from one location to the another location. As mentioned in the previous abstract, many heuristic search algorithms are ineffective because they must be employed in the real time. It is not feasible for search algorithms such as A star or IDS star or PRS star to ensure that the amount of time spent planning each action will remain constant over time. The D star and ARI star and AD star are some examples for replanning algorithms that do not operate on the same manner. This is due to the fact that they must all provide a complete, uh, all if imprecise response before any action can be performed. This indicates that this is an issue grow in magnitude and will require more time for prepare for the solution. Can you go to the next one? They have discussed about sub-goal database construction. In this technique, which was shown in the figure 1, after converting the grid-based map, then the A figure to a graph, and in the B figure, the graph is actually abstracted to such that every clique of original states become a single abstract state. The process is repeated. On the C figure, the ground level state that is closest to the centroid of the clique is selected as a representative of the abstract state. After the abstraction process is completed in the whole figure 1, the representatives has been identified. The abstraction technique is done 3 times in a row, the first with a few little circles, and there are few little circles in the portion D of the illustration where ground level states that abstract to distinct abstract states are shown as zones of varying hues in the diagram. Can you go to the next slide? After this, the DLRTS star takes into the account and looks at all the pairs of abstract states that are in the same region of the map. For each pair, it finds the best way to get between ground level representatives of the two states that aren't real. In the next step, it shows how the path started and where it ends. It also shows where the path ends and where the path actually starts again. The marked state is stored as a sub-goal for the pair of abstract states that make up the pair of the abstract states that is actually mentioned in the figure 2. People have built the clique abstraction, find the ground level representatives, and run Jectra2 from the ground level representative that corresponds to the abstract goal state. Then trace the path backwards from the starting representation point. So DLRTA code is actually not very simple. Can you go to the next slide? So in this construction, the strategy KNN and LRTS star, which is used to build this database, which was shown in the figure 4, there are n things which we need to consider to do this map, that we need to make it, and then make this n pairs of the ground level states that can be reached at least by two to three moves. That is from line 3 to 5. In the code actually explains how this construction is happening using LNN, KNN, LRTS star. Can we go to the next slide? The runtime search. In this runtime search, if a particular aim is sought by an agent, he or she will have to make a broad generalizations based on the information that is accessible to him. The frequent yet straightforward approach of generalizing this at a runtime is the clay closest neighbors method. That is actually from Cover and Hart 1967. It ultimately boils down to the pulling together solutions from the variety of comparable scenarios and utilizing it as a solution for the problem at the hand. When looking at these maps on the right side, the term heuristic distance typically refers to the technique that may take to your destination. Depending on your preference, the Euclidean distance and the Manhattan distance or the octahedral distance may be used. The natural application of this Manhattan distance is the diagonal operations. There don't seem to be any obstacles on the map that may cause this distance to be greater than they are already. Can you go to the next slide? So coming to the properties, their sub-goals may be determined as that shown in the line 12 of the figure 7, or LRTS star or KNN LRTS star as shown in the figure of the line 13 of figure 7. So this line 3 to through the 7 are the examples. The former is able to satisfy the time restrictions of the real world, but later cannot. So Karf 1990 is the guy who actually introduced this. And in this line 3 to through the 7 of the second example will demonstrate that it also compiles with the criteria, since the amount of CPU needed by these lines does not increase endlessly as the map size increase. Because the database size, that is n, is independent of the map size, all the hill climbing experiments are bound to be by this parameter. In the worst case scenario, all the items in the database will be calculated from the similarity and the hill climbing reachability in the time complexity of O of m of n time, and the results is shown. Results will be shown. The asymptomatically memory insensitive subgoal database, that is O of n, the LRTA star heuristic. There is a tabu list of T of O of n that are those are all examples of memory insensitive algorithms. Can we go to the next slide? In the empirical evaluation, coming to the figure 8, which was present in the right side, you can see the results of both the test, both the DE LRTA star and KNN LRTA. The subplots in this figure shows the path of that aren't ideal for the agents they control, filled with markers. If the ideal path costs 100, erode with that cost 110, which is 10% ideal. That is an ideal path. This is how the cost difference between the best and the worst path are shown. It is better to use the points that are closer to start. Can you go to the next slide? Yeah, so this is how the DE LRTS star suboptimally changes depending on the level 3 of abstraction. For the third and fifth level, it is better than KNN LRTS star. But when you are coming to level 3 subgoal database, DLRTA needs lot of RAM, that is 8 map sizes to work. So one of the graph shows that the DLRTA 3 star in the left subplot and the KNN LRTS star, that is of 1000 in the right subplot, have data points outside of the range shown in them. It expands to 42 states per move. For example, you can find the parameters of the LRTS star and the KNN and the LRTS star on the page 1 of the table 1, which was there in the right side of the presentation. You can also find the conventional LRTA star. Each column has a following information, that is time, size, which is the time it took to make a subgoal database, and how big it is compared to the size of the map, how bad the solution is, and how many states are expanded every move. Can we go to the next slide? So coming to the conclusion, in this study, the major motivation of the authors was to design a new high-performance real-time search algorithm, where DLRTA is a current state-of-art real-time search algorithm and has a lot of memory requirements for the pathfinding in the video games. But the work aims to make DLRTA less memory insensitive so that it can be used in the video games. So LRTA star is a popular algorithm for pathfinding in the video games. The new KNN LRTS star has many advantages over DLRTS star. For example, the new algorithm is very easy to implement than the DLRTS star because it doesn't need much memory to store the subgoal databases. AI algorithms in the video games should be easy to make and have more memory footpoints. Can you go to the next slide? So coming to the conclusion of the presentation, we have discussed three tree search algorithms, LRTS star and NLRTS stars. Both are compiled. The LRTS star and NLRTS star algorithms are using variety of objectives to plan optimal and near optimal paths. Both algorithms are actually capable of identifying large number of objects that are close together. In the second paper, that is KNN LRTS star, and that is for simple subgoaling for real-time search star. The DLRTS star, a current state-of-art real-time search algorithm, actually has lot of memory requirements for pathfinding in the video games. They have introduced a new algorithm, that is KNN LRTS star, of modifying the LRTS star, which is actually a popular algorithm in the pathfinding of video games. That'd be all for today. Thank you, guys.